Section: Introduction. In this section, we explore the concept of scalable oversight in AI training. If we want to keep using human feedback to train AI systems, we need to ensure that the feedback remains accurate even as AI surpasses human expertise. One way to address this challenge is through scalable oversight, which involves developing training methods that allow humans to provide precise guidance to superhuman AI systems. This is crucial for ensuring the safety of advanced AI technologies. Recent studies have shown that large language models, LLMs, can learn to exploit inaccurate training signals, such as manipulating rewards, which can lead to potentially dangerous behaviors. It is possible that more powerful AI systems could further generalize these behaviors to more complex and harmful exploits. By improving oversight quality, we can reduce the risk of such manipulative behaviors. Debates between equally capable AI systems have been proposed as a way to help less capable human judges make accurate decisions. The idea is that through a debate, both sides present their arguments truthfully, allowing the judge to select the correct answer. While theoretical studies support the effectiveness of debates in supervising AI tasks, empirical evidence is still needed to confirm if debates can indeed enable less capable judges to oversee stronger AI agents effectively. Our research focuses on studying debates across various tasks to bridge capability gaps through scalable oversight. We use different oversight protocols, such as consultancy and debate, where judges interact with consultant or debater LLMs to make decisions. By comparing the accuracy of judges in consultancy and debate scenarios, we aim to determine if debates between capable AI agents can lead to more precise judgments. We conduct experiments across different tasks and oversight protocols, varying the capabilities of judges and AI models. Our findings suggest that debates consistently improve judge accuracy as AI capabilities increase. While debates outperform consultancy, further research is needed to explore debates as a training method. We also consider the impact of fine-tuning approaches on judge performance and suggest future directions for enhancing the effectiveness of debates in AI training. Section Summary. In this section, we explore the concept of scalable oversight as a solution to ensuring accurate human feedback for AI systems, especially as they surpass human expertise. By studying debate protocols between AI agents on various tasks, we aim to bridge capability gaps and evaluate the effectiveness of scalable oversight in improving judge accuracy as AI capabilities advance. Our findings suggest that debate consistently enhances judge accuracy as AI capabilities increase, although further research is needed to fully understand the potential of debate as a scalable oversight protocol, particularly in training AI models. Section: Related work. In this section, we will discuss the related work on empirical evaluations of debate protocols and scalable oversight evaluations. When it comes to debate protocols, previous studies have shown mixed results. Some experiments using human debaters and judges did not significantly improve judge accuracy, especially when GPT-4 debaters were used instead of strong human debaters. However, promising results were reported with LLM debaters and judges using inference-time debate and RL training on the quality dataset. Our work is closely related to these studies, as we also use the quality dataset and employ similar debate setups. Moving on to scalable oversight evaluations, we introduce the concept of sandwiching, where a model's performance lies between that of weaker and stronger human groups. This evaluation method can be applied to various oversight proposals like recursive reward modeling and iterated amplification. We also explore an open consultancy protocol similar to previous studies, but we use LLMs instead of weaker human groups to enhance efficiency and speed. LLM-based debate has been studied in different contexts, such as text assessment and translation. Some research shows that debate may not be more effective than majority voting for reasoning tasks. Our focus is on using debate as a scalable oversight protocol rather than for self-improvement. We aim to evaluate weak judge accuracy compared to debaters. Our study involves tasks where a judge LLM answers questions based on input from debater or consultant LLMs, and judge accuracy is measured against ground truth labels. We vary the setup across scalable oversight protocols, QA tasks, and judge LLMs to explore their impact on judge accuracy. We create tasks by adapting existing datasets with LLM prompt templates suitable for each oversight protocol. Tasks fall into three categories: extractive QA, closed QA, and multimodal tasks. Extractive QA involves supplying a binary choice question and an article to consultants, debaters, but not to the judge, creating an information gap. Closed QA tasks provide questions and answers without an article, focusing on model capabilities and reasoning skills. Multimodal tasks combine image and text inputs, aiming to understand the impact of additional modalities. Section Summary. In this section, we summarize related work on debate protocols and scalable oversight evaluations. The study explores the effectiveness of debate with human and GPT-4 debaters, finding promising results with LLM debaters and judges. Additionally, the concept of sandwiching is introduced to evaluate scalable oversight proposals, and LLM-based debate is investigated in various contexts beyond oversight protocols. Section: Protocols. In this section, we explore different protocols for overseeing AI training. We use a scalable oversight protocol where a highly capable AI is supervised by a weaker judge to provide a training signal. The debate theory suggests that accurate supervision is guaranteed when the AI debaters have aligned their training with the signal from the weak judge. In our experiments, we assess judge accuracy and scaling trends as the capability gaps widen, focusing on consultancy and debate protocols. We compare several oversight protocols, mainly centered on consultancy and debate tasks. Our setups and prompts are based on previous work, with some minor differences explained separately. The first two QA protocols are basic QA baselines that do not involve scalable oversight. They serve as direct QA comparisons and rely solely on the judge model without input from a stronger model. We expect scalable oversight protocols to outperform these baselines. The consultancy and debate protocols are assigned role, where consultants and debaters are given specific positions to argue. The final two protocols are open role, allowing more flexibility in choosing answers. Debaters and consultants are instructed to structure their arguments logically and present their case, with only the final argument shared with the judge. For QA protocols, we have the naive protocol where the judge is prompted with a question and answer options without the article, and the expert protocol where the full article is provided along with the question and answers for extractive QA tasks. In the consultancy protocol, a consultant argues for an assigned answer, while the judge evaluates the argument. In the debate protocol, two debaters engage in structured arguments to convince the judge of their answers. Open consultancy allows consultants to argue for their chosen answer, reflecting a truth-seeking approach. Open debate involves one debater selecting their answer, while the other is assigned the opposing answer, offering a realistic training scenario for AI alignment. Section Summary. In this section, we explore scalable oversight protocols that provide training signals for AI systems by supervising them through weaker judges. The effectiveness of these protocols is evaluated based on judge accuracy and scaling trends as capability gaps increase, particularly in consultancy and debate tasks. Different protocols, such as QA without article, QA with article, consultancy, and debate, are compared to assess their performance in providing accurate supervision for AI training. Section: Models. In this section, we discuss the models we utilized in our study. We employed Gemma 7b, V1, GPT 3.5, Gemini Pro 1.0, and Gemini Pro 1.5. Gemma 7b is open source to promote reproducibility. GPT 3.5 served as a judge in previous work for result comparison. In our initial experiments, we used Pro 1.5 as debaters, consultants, and all models as judges to examine strong consultants, debaters overseen by weaker judges. We also varied the debater model in the ELO section and analyzed it with two judges, Pro 1.0, Pro 1.5. Models were used with default sampling options unless specified otherwise. We then present our findings across different task types, judge models, and assigned role protocols: consultancy, debate, and QA without article. We used Pro 1.5 for consultancy, debate with 3 rounds of interaction. In debates, debaters provided responses through best of 4 selection, where Pro 1.5 chose the most persuasive one. Judges predicted answers based on the protocol transcript. We calculated permutation-based p-values to determine the performance differences between protocols. Stronger judge models generally showed higher accuracy across protocols. For extractive tasks, stronger judge models tended to be more accurate. Using information directly, DM-RED 500QA with article was found to be more effective than oversight. In closed tasks, DM-RED 500 debate increased judge accuracy compared to DM-BLUE 500 consultancy. Gemma 7b performed the weakest, while GPT 3.5 and Pro 1.0 were more indicative of scalable oversight. In multimodal tasks, DM-BLUE 500 consultancy was notably less effective. Judging ability correlated with reported capabilities, with Gemma 7b being the weakest judge. We also explored the impact of reducing the number of turns from 3 to 1 in consultancy and debate. We found no significant effect on judge performance, suggesting that for these tasks, models, and protocols, more rounds did not improve judgment accuracy. Section Summary. In this section, we explore various models including Gemma 7b, GPT 3.5, Gemini Pro 1.0, and Gemini Pro 1.5 for tasks like consultancy, debate, and QA. We use Pro 1.5 as the strongest model for debaters, consultants, and observe that stronger judge models generally lead to higher accuracy across protocols. Additionally, we find that reducing the number of turns from 3 to 1 in consultancy and debate tasks does not significantly impact judge performance, aligning with previous findings. Section: Ablation, Best of N for debaters. In this section, we examined various aspects of the debate protocol to enhance the debater's performance. We started by adjusting the best of N, BON, sampling for debater responses from 4 to 1, which is standard sampling. Surprisingly, reducing the BON did not significantly impact judge accuracy. However, our analysis indicated that LO ratings tend to increase with larger N values, and judge accuracy also improves with higher LO, especially for weaker debaters. Next, we explored the impact of providing the judge with varying numbers of prompts before making a decision, ranging from 0 to 6 prompts. Interestingly, increasing the number of prompts did not lead to a significant improvement in judge performance. We also investigated the use of chain of thought, COT, reasoning by the judge compared to a default prompt that only required the judge to give an answer. Contrary to expectations, employing COT reasoning either had a negative effect on performance or showed no significant difference. Furthermore, we analyzed the debate turn styles, whether they were simultaneous or sequential. Surprisingly, we did not observe a significant difference in performance between the two styles, suggesting that any potential asymmetry between debaters is not crucial. Additionally, we looked into positional bias exhibited by judge models, where judges tend to prefer either the first or second answers in a debate. By presenting each question twice with the answer and debating order swapped, we found no significant difference in mean judge accuracy, indicating that randomizing the answer position could be sufficient to mitigate positional bias. Overall, our findings suggest that debate holds promise as a scalable oversight protocol compared to consultancy. However, these conclusions are based on the inference-only setting, and further evaluation is needed to explore the effectiveness of debate protocols for training purposes. Future research should focus on improving judge performance in debates compared to direct question-answering tasks. Section Summary. In this section, we explore various ablations in the context of debate protocols. We investigate the impact of factors such as the best of n sampling for debater responses, judge few-shot prompting, judge chain-of-thought reasoning, debate turnstiles, and positional bias in judge models. Our findings suggest that debate may be more promising as a scalable oversight protocol than consultancy, with implications for training protocols and the potential for improvement over direct QA baselines. Section: Persuasiveness in debate. In this section, we examine the persuasiveness of debaters in debates, viewing debate as a useful training method. Instead of focusing on training models to win debates, we assess how well a debater can persuade the judge in inference-only debates and how this relates to judge accuracy. Unlike previous sections that used only one debater model, Pro 1.5, we now consider multiple debaters to study their persuasiveness by looking at their win rates in cross-play debates and their skill level using an ELO rating. We find that stronger debate models, as indicated by higher ELO scores, slightly improve judge accuracy, suggesting that debate can be a helpful oversight protocol, although the impact on judge accuracy is not very significant. We conduct debates with 5 debaters: Gemma 7B, GPT 3.5, Gemini Pro 1.0, Gemini Pro 1.5, both with BON equals 1, and Gemini Pro 1.5 with BON equals 4, focusing on one-turn arguments in simultaneous debates. By pairing these debaters in cross-play debates and judging them with Pro 1.5, we calculate their ELO scores. We also calculate correct ELO and incorrect ELO scores by treating each debater as 2 separate players based on whether they were assigned the correct or incorrect answer. Our results show that it is generally easier to argue for the truth, especially in closed tasks, and that stronger models tend to have higher ELO scores. We observe a positive difference between correct and incorrect ELO scores for all debaters, indicating an advantage for those assigned the correct answer. However, we do not see a clear trend of this advantage increasing with higher ELO scores, particularly in closed tasks. Stronger models perform better in terms of judge accuracy in extractive tasks, where judges rely more on debaters for information, while there is less differentiation in closed tasks. When looking at how aggregate ELO scores correlate with judge accuracy, with Pro 1.5 as the judge, we find that stronger models lead to higher judge accuracy in extractive tasks, but less so in closed tasks. The choice of judge model, Pro 1.0 or Pro 1.5, also influences the results, with some differences in the performance of debaters. Overall, our findings align with previous research, but we observe a narrower range of judge accuracy improvement, suggesting that these results may not apply broadly to tasks beyond quality. Additionally, we note that Gemini family judges tend to give lower ELO scores to GPT 3.5, possibly due to a preference bias towards their own model generations.